Okay, so hello everyone. So this is part two of my video on descriptive analytics, nature of data, big data, and statistical modeling. Where in the first part we discuss about the nature of data and the essence of big data. Today we'll be discussing about the technologies behind big data and the statistical modeling techniques discussed in the chapter. So before we go into big data, we need to define the parameters or the infrastructure behind big data itself. Now, the infrastructure needed for big data is by high performance computing, where we have several parts of its infrastructure, or several kinds rather. First is in-memory analytics, where the computations are done in RAM or in memory for near real-time insights. Now, the second kind of infrastructure is the in-database analytics. Data integrations and analytic functions performed inside the database. Now, the main difference between these two is that the in-memory analytics is performed inside the memory. So the RAM in your computer holds this memory or the data itself. Now, this is common for pandas, for other data frame libraries, but for more real time, not real time, but for more in depth kind of analysis, where especially the data is really big and it doesn't fit inside the RAM, you make use of in database analytics. Now, the third one is the grid computing. The grid computing is shared, centrally managed pools of IT resources. We commonly see grid computing for parallel analysis. So you have lots of databases, but part of the same database structure. So basically, this is horizontally aligned, where the in-database analytics is vertically aligned. Where in database analytics, you have one main server, and for grid computing, you have a lot of smaller computers that holds a database or parts of the database. Now, the appliances for this is that it's fast, or the application of this rather, it is fast and scalable integrations of both hardware and software. Now, for the technologies of big data, there are lots of technologies that is already within the industry, and these technologies are used in commodity for hardware for scale out parallel processing. So we see these in Spark, Hadoop, Cassandra, Hunk, Kafka, etc., etc. Now, there are three main technologies, and these technologies, by the way, are technologies that holds the database itself. And these technologies are also used for the pre-processing. And the main technologies for these are Hadoop, MapReduce, and NoSQL. Now, for the first technology, Hadoop, Hadoop is an open source framework for processing, storing, and analyzing massive amounts of distributed, unstructured data. Breaks up big data into multiple parts so each part can be processed simultaneously. So this is an example of grid computing where there are many computers performing the same task or querying from the same database. Now, the core components include Hadoop Distributed File System or the HDFS, name nodes, and the job trackers. And this is the MapReduce. And this is one of the core components of Hadoop, where this is a model popularized by Google, and it's a core element for parallel processing for Hadoop. The map program splits and groups data, and the reduce program aggregates the result to find the final answer. So we start by querying using multiple computers, aggregating them, then get the final answer. So we see the flow chart here. And the Hadoop ecosystem is as follows. First, we have Hive. This is the main data warehousing framework using a SQL-like language, mainly HiveQL. We have Pig, a query language adept at very deep, long data pipelines. HBase, a non-relational database for low latency, quick lookups. And we also have Flume. This populates Hadoop with data via agents inside web and application servers. So Flume is also used, by the way, for new AI applications that make use of agentic workflows. Uzi is a workflow processing system linking MapReduce, Pig, and Hive jobs. So Uzi is the orchestrator. MAOut is a data mining library utilizing MapReduce. So this is used for web scraping. And Scoop moves data between Hadoop and traditional relational databases, especially when transitioning from traditional databases into the Hadoop ecosystem. Now, we also have Spark. Now, I didn't discuss Spark here, but Spark is mainly a version of Hadoop where it mainly uses in-memory processing. Now, these are o- both are open source Apache frameworks, but Spark uses in-memory processing. Spark is much faster for real-time and stream data analysis. Hadoop, while Hadoop relies on disk read or write operations. As you can see on the right, these are the main differences. You see that Hadoop is for disk-based frameworks or those data sets that are stored in a database, well, whereas Spark is for memory-based frameworks for data stored in memory. And Spark is mainly used for stream-oriented data, so as data processed in real time, whereas Hadoop is processed by batch. And Spark is a general purpose framework and is commonly used now for machine learning models, especially when training data, whereas Hadoop makes use of the MapReduce framework where it sends out a command, aggregates, and get the data. Hadoop is scalable, reliable, and compatible for most systems, whereas Spark is just fast, easy, and versatile. And Hadoop is suitable for batch and historical analytics, especially for large datasets with temporal perspectives, whereas Spark is suitable for real-time and interactive analytics. So when do you use Hadoop versus Spark? We use Hadoop to process sets exceeding available memory, especially if your memory is more than 8 gigs, 16 gigs, or 32 gigs, and is used for batch processing, building the analytics on a limited budget, and analyzing historical archives. Whereas we use Spark for in-memory computations, real-time stream analysis, graph parallel processing, and machine learning operations. And the third technology, NoSQL databases, stands for not only SQL. This is aimed at serving discrete data among large volumes of multi-structured data to applications. And unlike with the traditional SQL databases or relational databases, this does not make use of a relational table and join statements, but rather we use NoSQL to map out the data directly. This creates ECID compliance for high performance and massive scalability. And examples for this are MongoDB, which is the industry standard, and Cassandra for real-time processing. Cassandra is used, by the way, in Discord, and MongoDB is used by a lot of platforms. And we also have data for good. So this is a movement utilizing crowdsourced public data to solve socially and environmentally meaningful problems. So the main movement of this is that the notion should be data should be free, especially for solving critical problems that are socially viable and environmentally viable. Now, examples for this include DataKine, TIBCO for Good, and SAS Data for Good. This aims to tackle humanitarian issues around poverty, health, and human rights. Now, we also have big data in the form of stream analytics. We have where we define stream analytics involves the extracting actionable information from continuously flowing data. So these are data with high velocities happening in real time, especially for sensor-based data like you can see here in the in the smart grid analytics diagram, where you have sensors sending the data directly to the database. This analyzes a window of data consisting of continuously updated tuples or datasets. These are essential because time to action has become an ever decreasing value. Now, the application of stream analytics are the following. We have e-commerce, like real-time click stream analysis to offer targeted bundles and prevent shopping cart abandonment. Telecommunications, such as churn prediction via call detail records or CDR. We also have the power industry, analyzing smart meter data to optimize energy supply chain decisions. And we have the financial service, where high frequency trading and real time fraud detection is performed. So that's it for the applications of big data. Now we talk about statistical modeling for business analytics. We describe descriptive analytics as two main branches, mainly statistics and OLA. Now, statistics helps the characters data one variable at a time or multivariably, and this is divided into descriptive statistics and inferential statistics, and this framework now is divided into both descriptive and inferential statistics, where we are describing the data at hand for descriptive, and we are drawing conclusions about something, or in this case, populations, for inferential statistics. Now we have the measures of central tendency. So we have the basics. We have arithmetic mean, which is the sum of all values divided by the number of observations. But take note that the arithmetic mean is very sensitive to outliers. Now the median is the middle value of an ordered dataset and is completely unaffected by outliers. And the mode is the most frequent observation in a dataset, highly useful for nominal data. Now we have measures of dispersions or variance. We have the range, which is the difference between the maximum and minimum values. We have the variance, which is the square deviation of data points from the mean. Also have the standard deviation, which is the square root of the variance expressed in the same units as the data. And the interquantile range represents the middle 50% of the data, where we subtract Q3 minus Q1. So this is the third quantile minus the first quantile. And popularizing this range analytics or this variance analytics, no? Or yeah, dispersion is a box and whiskers plot, which shows the variance of the data set. So this is developed by John W. Tukey, and this visualizes the centrality, dispersion, quartiles, minimums, maximums, and outliers. The box represents the middle 50% of the data. Whiskers represent 1.5 times the upper or lower quartiles. And we also have the shape distribution, especially for continuous data sets. We have where we have two main points. We have the skewness and the kurtosis. The skewness measures the asymmetry in a distribution, where a positive skewness has a long right tail. Sorry, this is long left tail rather. And the negative skewness is the long right tail. Ah, sorry. Sakto eh. Na, bali lang ang figures. Hmm. Ano sakto eh? Positive skewness is long right tail, so elongated tail. And the negative skewness has a long left tail, so like this. It is elongated. And the kurtosis measures the degree to which a distribution is peaked or tall or flat or short compared to a normal distribution. So this basically measures how much of the data is going towards its centrality or its mean. So if you have a positive kurtosis, it's more peak. For a normal distribution, it's relatively a bell shape. And a negative kurtosis is more or less flatter. And we also have regression modeling as one of its tools for business analytics, where the regression captures the functional mathematical relationship between explanatory, the input variables, and a response, the output variables. So this explanatory is also the independent variables, and the response is the dependent variables, where we also use for this is also used for hypothesis testing and prediction or forecasting. Simple regression has only one input, whereas multiple regression or multilinear regression has multiple inputs. So we have a simple example here where we're using only one input. Now the assumptions for linear regression is that first, Relationship between variables is linear or linearity. Second is independence. Errors of the responding variable are uncorrelated. So basically, these should be this should not express multicollinearity. Third is normality. Errors are normally distributed. Fourth is that they have constant variance. Errors have the same variance or homoscedasticity. And multicollinearity. Explanatory variables are not perfectly correlated with one another. Sorry, for independence, this means that there is no multicollinearity between the independent and the dependent variables or the observation and the target, whereas the multicollinearity expresses that there should be no collinearity between the independent variables. We also have another form of logistic regression where we of regression, namely the logistic regression, where this is a probability-based classification algorithm. So this deviates from the usual regression stereotype where we're actually getting a value. But this time for regression, this is mainly used as a classification, where your zeros are one classifier and your one is one classifier, as shown here. This predicts categorical outcomes, often binary, like yes or no, pass or fail, rather than continuous numerical variables. And this takes the natural logarithm of the odds to create a continuous criterion for processing. And lastly, the time series forecasting is a sequence of data points measured at successive uniform time intervals. And the model extrapolates time varying behavior like random variations, trends, and seasonal cycles to predict future values. Now, techniques include simple average and moving average, and complex method like ARIMA and SARIMA. Okay, so this is everything for descriptive analytics part one, and I hope you learned a lot from me. Thank you.